All right, good afternoon, ladies and gentlemen. Welcome back to InnoVEX Center Stage. AI is bringing a new wave of technological innovation and development to our world. And today, the forum is hosted by AITA, which is Taiwan's leading AI chip manufacturing, exchange information that connects the software ecosystem in Taiwan. Today, we're honored to invite experts from the leading international AI manufacturer to deliver keynote speeches focusing on the theme of driving innovation of AI on chips. To begin with, I would like to first invite the organizer, the chairman of AITA, Nicky onto the stage for an opening speech. Let us welcome Mr. Nicky Liu.
I hope I won't block you. Is that all right? You can see the screen? Okay. Welcome to Computex, and especially welcome you to attend our AITA symposium or workshop, whatever. AITA represents AI on chip Taiwan, means AI plus semiconductor, which will be a few tips I will present in the following. My name is Nicky Liu, and my vice chairman is Dr. Professor Chang. And thank you for many supporters from industry and our staff to prepare this afternoon. I hope you can enjoy it. So I selected topic as the major theme for this forum: driving innovation with AI on chips. Next. Okay, 1.5 years since ChatGPT announced their results, the whole world was shocked. But actually, Taiwan started AI on chip 2019. We have 4 years to prepare that moment come. And now we are ready and hope you come to Taiwan or we go to your place to collaborate it, to wait for a big, big time, larger than cell phone, larger than PC, even larger than mainframe computing. I used to work for IBM in 80s. I built an 8-inch wafer there, 8-inch wafer in Taiwan. Now, Taiwan has 12-inch wafers serve you, but I think most important, I will show you that the fortress Taiwan has been built after we have our own manufacturing and design technology. So anyway, this is, I think most people probably see this, but I want to repeat it. Diffusion in transformer, converting token into intelligence action. Please. Silent, but this was generated by AI, by a company with Sora programs. Next. This time, sound effects by 11 Labs. All amazing. Text converted to text with constructed tokens and convert to video. But I almost missed the time I should speak because I'm playing a major song for our talk. Playing many songs and pick up this one because they give that album cover, which I don't know why. The other company is more practical, give me all the circuit and printed board. And I think in the future, we should have this kind of things. It's a mystery for me, but I'm going to that mystery palace to see what happened. But you heard the sound, that's basically converting my every word into the sound, beautiful sound. There are also by voice, by chorus, by choir, whatever, I select this one. So amazing. Next. Okay, I promote intelligence power to end times. Not just AI, it's intelligence. 10 years ago, and we believe that intelligence and civilization was created. I'm surprised it's coming much faster than I thought. But it was coming more and more. We cannot imagine. So a lot of I don't know why the God like AI, IoT, HI, heterogeneous integration, IC, semi, with focus on no longer the die size, focus on function, value, and I think most important is power cooling, power efficiency, okay? So, pervasive intelligence era. It's not just like a scientist or technology or industry people. We enjoy it. It's pervasive. Everyone. Just like people enjoy cell phone today. I think AI become pervasive very soon. Okay, music already start. Okay, so many things. So let me briefly say, don't forget human brain intelligence. I cannot present you more because this is just an opening remark. But don't forget our brain. So I suggest you watch a movie called Lucy. Okay, this brain is very bad. But on the other hand, it's very good. Only 15% intelligence, but it creates the level of intelligence with much less power. Million times, even more than AI. The third one is cell intelligence. Now DNA become like our tool, like micro robots, like many things. Taiwan just announced their new regulation or laws for doing DNA work in Taiwan. Aging intelligence. We want to be young. I think we can be young. And the environment intelligence, human did very badly to environments. But all of us today, we swear that we will do good things for Earth. Okay, I told my colleague, in the last 40 years, I devoted my career to semiconductor. I was always be applauded. If we don't do it correctly with AI plus semiconductor, the next few years of my career will be blended by many people. You waste my power, you make the world so hot, etc. Space and Earth interface. So anyway, I just want to introduce you. If you are not doing semiconductor, that's all right. If you are not doing AI, that's all right. Your domain knowledge can become so important than ever before. Next. So just roughly to present it, 10 killer applications, but actually, you know all this. I just want to emphasize with these 5 I's, actually the foundation is AI plus semiconductor. No doubt. Look at the Computex keynote speakers. This is a system conference. However, the keynote speaker all coming with their background semiconductor, like Jensen Huang. But now they step into microsystem, and some step into system. On the other hand, the data company coming from system side come to Taiwan. I will give you why. Next. Okay, so I'm very glad many of the colleagues and from our industry start the efforts, I would say, collectively. With no antitrust. By the way, we never talk about real business. They know each other, then they talk business on the other side. But in our platform, every week, we have some group meeting to transfer, especially from Professor Chen of ITRI, what's going on in the world, what's going on in Taiwan, and how you company can may or want to collaborate. Next. So today we have 153 members with various AI knowledge from system integration applications like Microsoft, many others, IC design like MediaTek, Fab, okay, like UMC, packaging, like ASC, software, like Cadence, Synopsys, Association, VC, Academia. You wonder why Fab TSMC didn't come. That's the problem, you know. I believe many of you have been the champion and #1 in your class. One thing, people jealous you, we are not jealous of them. But they worry that you stole the information, I guess. So Dr. Chen, we have to talk to TSMC, okay? In my world, the only thing we know is moving straight ahead. No secrets. No intelligence will become secret. So if you cannot move ahead, so TSMC will join us soon, okay? But look at this. Amazing. Next. And this is the final, the last third chart. Why people come to Taiwan? I draw this diagram, not diagram, the whatever. Because all this work like a fortress, castle, with various know-how, various training engineers and administration people. They come here for this. Look at that. Okay, we have very central AI study. On the left-hand side is cloud server. We don't build server, but we, in the support like health or energy, we support this data company to come to Taiwan, interact, working together. However, on the right-hand side, 5G, IoT, FinTech, Taiwan has pretty good foundation. We have a lot of good bankers which work like entrepreneurs. And then we have information communication technology. That's this conference. But electrical, sorry, it's typo. Electronic. By the way, we never use AI to check our spelling. Wow. Heterogeneous integration, that means we put die by die inside one package. Because they are so close to each other, they burn less power. Their speed was not be delayed by motherboard. So Gordon Moore said 30 years ago, he said, integrated circuit, not only the Moore's law, but it worked like a Pac-Man, continue to bite. And heterogeneous integration, I proposed in year 2000 because Etron invented and really realized it, known good die memory. SRAM, DRAM, without failure bits, just like you put the memory in the package. And we don't need that. Practically, we sold to TSMC, they manufactured for me, and I sold to Intel. Intel gave me the best supply award. But I want to say, importantly, scientifically, theoretically, and practically, silicon plus silicon dioxide system can afford just use bare die. So you have whatever other technology, like gallium arsenide, photonics, please think about how you put your die on the platform like CoWoS or other substrate technology. You can merge them, bare die. So Taiwan, since year 2000 up to today, it's 24 years. We understand heterogeneous. So when we build packaging, module, server, heat, dissipation, like Jensen Huang said very clearly, he had to come to Taiwan as Taiwan subcon to use water to cool down the server instead of the old conventional method. We need to have invention to change that. In microsystem, we have IP service, many good companies I built, including GUC, Global Unit Chip Corporation. Professor Chen, also my consultant. We built the top world design service company. We call Design Foundry. Now they operated by TSMC with 42%. Before they joined us, I own 100%. After that, I own 25%. But today, their stock is too high. I sold some of them. That tells you, in Taiwan, nothing has been theoretical without going to practical. And nothing impractical without theoretical basis. That's what, before this meeting, we have people in the VIP room. I told Professor, your time come. Invention is your best. Then look at the vertical integration. We have foundry like TSMC. They are not doing foundry wafer. They also do the CoWoS. So this is called fortress. That's why people have to come to Taiwan. I admire Silicon Valley. I graduated from Stanford. I'm surprised that Silicon Valley is still top in the world. Look at the Jensen Huang, NVIDIA. Look at the Lisa Su, AMD. Of course, Intel and many others. Still Silicon Valley. But here is Silicon Island. We provide this kind of infrastructure. Okay? Next. So, AI plus semi is just like a semiconductor 30 years ago when I returned from IBM to try to build an 8-inch wafer for this island. Put them together, it's a new technology. Don't separate them. Okay? That's a key message. And we now have this infrastructure. We can do many things. So we start marching like soldiers. We're going to do many things. That's why you are here. Okay? Come to Taiwan, know people, and see how your things can be united or alliance or licensed or collaborated. What we are going to do, push the button, please, Justin. This is my favorite one. AI on chip are going to build this lighthouse. And using this with 360-degree integration. In addition to the technology we're familiar, I want to emphasize quantum, atomic, semiconductor, electrical engineering, AI, humanity, and privacy are the current next wave. So remember this chart, okay? Next. I want to elaborate more. AI plus semiconductor. AI plus semiconductor is a pathfinding and solution tool. They are not end of goals. They are tools. The end of goals is we create the application in variety domains to march, not our technology, to march human beings, civilization, with good parts. And we have to avoid the evil parts, including the whole picture. So I create a name, and I present to many top-notch people. They agree, SAQUAS. Semiconductor is first S, AI plus quantum become AQU. Autonomous, either drone, car, whatever. The last S is smart system. Aqua is the water of Greek. S, water, S is what you can remember. That Taiwanese AI on chip, the next integration efforts. Of course, we watch out. Our fortress, we can do service to you. So I don't repeat these pictures, okay? But I want to do is Etron is building the last one, this new software plus hardware quantized system. We support the robot company, build their eyes, build their motions with silicon chips. Because I know the domain knowledge, and I try to understand the system and I'll build the chips. So final picture. Taiwan started semiconductor 40 years ago. With our government push, and industry received. What I want to show you, 1975, university start fab, lab. 1987, we do have engineers and built the TSMC. 1990, national submicron project, just like AI on chip, this kind of, but they have funding. 1991, I returned from IBM to Taiwan, founded my own company, Etron. I architect the 8-inch wafer technology they need, but it's not IDM, integrated design manufacturing technology. That's what Intel, IBM are still using their way. But Taiwan in 1990, I designed the ground rule to link process and circuits and application by using foundry design rule. That's why Taiwan, after 7 nanometer, moved much faster. Because if you don't follow the Moore's law, are you guilty? As long as you make things work faster, better. Of course, we like Moore's law. So look at from 10, I think $1 billion, 1991, $1 billion. We built a fab in 3 years. To today, we are 160 billion. So if you take, I will take serious number is 95. So 40 times increase. I'm not trying to talk about the history. I'm saying, I feel AI plus semi, plus HI, plus application domain, it's just like I'm working in Taiwan in 1991 to 95. 4 years, just like AI on chip, 4 years. And now, we're ready. And this time is different. Can we increase by 40 times after 20 years? My answer is yes. So thank you very much for listening. Thank you.
Let's give Chairman Liu the round of applause for his incredible opening speech. Please return to the seats with care. Thank you once again. Up next, I would like to invite Mr. Wei-Chen Chiu, the Deputy Executive Secretary of Office of Science and Technology Policy, OSTP, from National Science and Technology Council, NSTC, to give an opening remark. Welcome.
Hello, everyone. Thanks for Chairman Liu for bringing us such a inspiring open remarks. Right. And by the way, my opening remarks will be not that interesting or inspiring because I just recently joined the government to serve our country, and I just realized that as an officer in the government that I cannot, I have to follow some regulations. So later, if you see me watching this screen to read the draft, don't blame me, okay? But anyway, ladies and gentlemen, I'm Wei-Chen Chiu. It's my great pleasure to be here and on behalf of the Office of the Science and Technology Policy under the National Science and Technology Council of Taiwan. And I would like to extend my congratulations and support from, for this international forum organized by the InnoVEX and also the AITA. Okay, so our office, OSTP, collaborated with the Ministry of the Economy Affairs in 2019 to launch the AI on Chip program. And that is where the AITA Alliance, which is the AI on Chip Taiwan Alliance, is established to create an AI on Chip application ecosystem. Okay, so currently the AITA, just as Chairman Lu mentioned, that the AITA Alliance has over 160 members, and it becomes the significant platform for industry, for academia, and research units in Taiwan to collaborate and exchange the AI chip technology. So here I want to thank the Chairman Lu again for his leadership and the efforts of the AITA team. Okay, so taking this opportunity, I would like to share with everyone the recent policies and also the significant achievements of the National Science Council, Science and Technology Council in AI and semiconductors. So firstly, in response to the insufficient traditional Chinese data for large language model and their inability to fully reflect the Taiwanese culture and values. So recently, I think around 1 year ago, NSTC launched the TIDE program. So I believe a lot of you have heard of this, the Trustworthy AI Dialogue Engine, last April. And they developed a large language model with Taiwanese characteristics. Okay, so over the past year, this project has yielded promising results and is also open source, so I believe a lot of you have tried it. And the model was publicly released for free use in April this year. So moving forward, we will continue to refine the type model and develop more diverse application cases and expand the domain of its implementations. So secondly, the NSTC introduced Taiwan AI chip-based industrial innovation program, abbreviated as a CBI program, a 金创计划 in Chinese, last October, and in which this program plans to invest 300 billion new Taiwanese dollars over the next 10 years. So to not only propel our IC design industries to new heights, but also to drive the integration over the chips and generative AI across various industries. So in early May this year, so NSTC officially established the program office of the CBI to serve as a platform for communication among industries, government ministries, academia, and research sectors, monitoring both domestic and also the international industry trends and adjusting execution strategies accordingly. So thirdly, we are actively drafting the Artificial Intelligence Basic Act that will balance the innovation and the regulation. Okay, and hopefully we are able to provide a healthy and orderly environment for AI development in Taiwan. So finally, the NSTC will support and advocate for balanced and inclusive development as emphasized by our President Wei-Chen, collaborating with other ministries to support our domestic industries, not only in the technology sector, but also in traditional industries and small and medium-sized enterprise. I think it's extremely important that our high technology industry can help also our other traditional, no matter it's small size or medium-sized industries. I think it's more than important than ever. Okay, and so basically the rise of the generative AI has brought the great opportunity to leverage Taiwan's semiconductor advantage and AI to drive the industry upgrading and also the transformation. So in these emerging fields, the cooperation and exchange are crucial, basically. So NSTC looks forward for partnering with the industries to explore the infinite impossibilities brought by the artificial intelligence, ensuring that the Taiwan's industry leads in the era of the generative AI and promoting the development of our digital economy. So finally, thank you all for your participation, and I wish today's event great success. Thank you.
Thank you so much, Mr. Chiu, for your opening remark. Kindly remain on the stage. Today is really exciting, so we will have to remember the moment. Once again, I would like to invite the chairman of AITA, President Nicky Liu, onto the stage for a group photo. I would like to invite Chairman Liu onto the stage once again for a group photo taking. Up next, I would also like to invite the Deputy Executive Secretary Office, Mr. Chiu, onto the stage once again. VP of Cadence, Mr. Chen, as well as Director of NVIDIA, Mr. Wei-Chen. Deputy Director of MediaTek, Mr. Jenwei Liang, as well as Vice President of AITA, Mr. Shih-Chieh Chang, onto the stage to remember this exciting day together. All right, can we have the photographer to check if this standing is okay? Okay, can we look into the camera in the middle? 3, 2, 1. Of course, a thumbs up. AITA, super great. InnoVEX, super great. 3, 2, 1. We have some cameras on the left. How about we look to the left for our cameras on the left? Okay, thumbs up. 3, 2, 1. Not forgetting, right here on the right-hand side, we have many friends here who would like to remember this exciting day. Look on the right. 3, 2, 1. AITA, super good. All right, just remain on the stage. We would like to invite important chairperson from the important AITA 6 onto the stage to join for this group photo. I would first like to invite SIG 1 Chairman, Distinguished Professor of NCHU, Mr. Chang onto the stage, as well as SIG 3 Chairman, the Senior Consultant of SunPlus, Mr. Guo, to join in. SIG 4 Chairman, the Professor of NYCU, Mr. Tianfu Chen. Not forgetting SIG 1 Vice President Director of SunPlus, Mr. John Wu, as well as SIG 1 Vice President, the Vice President of Compal, Richard Xu. SIG 2 Vice President, R&D Director of ITRI, Mr. Guangning Chen, onto the stage, as well as our SIG 4 Vice Chairperson, Manager of Realtek, Mr. Ching Tong Wu. All right. Can I have all our chairperson and vice chairperson from all the important SIGs onto the stage? All right, is this standing position all right? Okay, let's look into the camera in the middle, right in the middle. 3, 2, 1. Also, another thumbs up for AITA and for InnoVEX 2024. 3, 2, 1. Okay, how about, sorry? Okay, we have a video. Do they need to move around, or a thumbs up is good? Okay, let's do a thumbs up outward, okay? 1, 2, 3. AITA, super good. We can move around, up and down. That's really, really exciting. We got the photos. Thank you all our guests, distinguished guests and speakers once again. Please return to the seats with care. Thank you. All right, our AITA Forum, exciting, is gonna begin really shortly. We have an incredible speakers lineup coming up next. So without further ado, I would like to invite the Vice President, Mr. Chang, onto the stage to give an introductory speech for our keynote.
Okay, welcome to the AITA Forum. This is actually the first time that AITA bring an international forum to InnoVEX. Also, by the way, we know that AITA is the AI on Chip Taiwan Alliance, but the pronunciation takes us for a long time because AITA, the pronunciation is very close to a lot of Taiwan, if you guys know that. As the chairman said that the purpose of AITA is to research, to explore and also to promote the technology of AI chip, hardware and software technology. Now today we are very honored, we are very happy to invite leaders, top executives from leading company to give us their cutting edge results. I think we will all benefit from their practical experience and their insights. So without further delay, let's begin this forum and let me introduce the first speaker. The first speaker is Don Chen. He is the Vice President in R&D at Cadence. He leads a global team responsible for advanced nodes deployment and support for the leading foundry in the world. Before he joined Cadence, he was with Synopsys. By the way, I also work for Synopsys, and we have some overlaps. Cadence has been supporting the qualification of IC talents and worldwide. So today, he will give us a talk on the era of multidisciplinary engineering fueled by today's AI and the ML demands. Please join me to welcome Don.
Thank you so much.
Okay, good afternoon. Thank you for the invitation and really very happy to be here today. So it's just amazing that the last 2 days just walking the floor to see what Taiwan Semiconductor has really done for the world. The amount of the innovations and devices that you see on the floor is just truly amazing. So, you know, one of the things that I was thinking that, well, I'm going to give a talk and it has to be AI and ML related. So one of the things that just like, you know, when you're going to battle, you really need to form a team formation in order to prepare for the battle. So I've decided to title my presentation to the era of multidisciplinary engineering. Because as you can see in the presentation that I'm about to share, we are about to enter a new domain, a domain that is new to many of us because we are used to doing designs in 2Ds. And you hear a little bit about today and yesterday's in the keynotes that now you really have to add functionality, you have to talk about 3D and so on and so forth. So this is really going to change the dynamics of team compositions that's going forward to get ready for the next generations of IC design. And since this forum consists of investors, startup companies, so I hope this talk will be very appropriate for the preparations for the next coming challenges. So to start off with, we hear a lot about AI and ML. So what is one of the common words that comes into play? We always hear the word prediction, right? When you're talking about machine learning, it's all about prediction. So many of you are familiar with this movie, The Terminator in 1984. You know, we have to give credit to the producers of this movie. So in that movie, if you recall, what was the prediction in this movie? Anybody want to take a guess? No? Okay, in the interest of time, let me give the answer. So the prediction of this movie was that in 2029, which is 5 years from now, the Skynet, which is an AI computer, is going to come back and really destroy the world. So the Terminator was sent back in time to 1984 to really take care of the situation. That is amazing, right? You know, you think of 1984, where Ethernet is not even widely available, and you have these movie producers that's making these predictions. And you know, 2029 is 5 years from now. And now we are all talking about AI, ML. So is that going to be a reality 5 years from now? We have to be very careful. And actually, this also brings responsibilities to ourselves, right? So AI, if used correctly, can do a lot of help to the human mankind. AI that's done incorrectly can cause problems. So I thought this would be a good lead into the talk that, you know, 5 years from now, we will think back whether this movie is correct, whether we have a AI computer that's going to destroy us or is going to help make our life better. Okay, moving along. So one of the things that you see that in the transformation of semiconductor, back in the 80s, there was only one of the driving force. The PC market was being introduced. If you all remember, the first IBM PC 4.77 megahertz is one of the brilliant desktop computer that's come along. And then the next driving factor was networking, and then followed by Ethernet, and so on and so forth. Today, why this is going to be different from what you see 20 years ago is that there are actually multiple drivers that's causing the change that's happening right now. You have 5G is needed to handle the large communication data. You have the hyperscale computing. We talk about GPU, CPU, and so on and so forth. And then you have the self-driving cars that's coming up. And all of us are talking about AI, ML. And then you also have the industrial IoT. So I think this transformation that's happening right now is not driven by one item alone. It is actually driven by a combination of multiple factors, and this is going to really pick up, and that's why the projection by the end of the decade, the semiconductor industry can potentially reach $1 trillion. And then if you look at the electronic systems that we are building, it will reach $3 trillion. So I think this is one of the reasons why we are all here, why we are thinking about AI and ML, why this thing is important to us, because all these are the driving factors that's going to push us and is going to cause more opportunities, more job opportunities, and more importantly, the software and the hardware really have to come to play in order for you to be able to accomplish such big goals. So then let's put things into perspective. Because if you look at it not too long ago, we actually went through a paradigm shift, whether you know it or not. So when we move from planar transistors to FinFET transistors, it actually causes us to change our design flow. We had to use different approaches because now the physical effects plays a very important role in the prediction of your entire silicon. So if you look at the picture on your left, you see that in the old days, you have the front-end engineers and you have the back-end engineers. After they are done with their RTL, they hand off the netlist to the back-end engineers that they have to implement and do a place and route. So what happened and what was the transformation that has changed? So new challenges drove the paradigm change. So the designs got much bigger, the process node gets smaller, and then you have synthesis to place and route correlation challenges between the front end and the back end, and then you have to deal with performance, power, and also the area challenges, and more importantly, the time to market, the whole turnaround time that's needed for you to meet your design schedule. So that actually forces the companies and the design teams to change their formation. So we move from front-end designer, back-end designer, to what now we call synthesis engineers and physical engineers. So more importantly, what really causes the change is the whole physical effect. So that was one of the transformations that actually just happened in the last 10 years. So now while we are getting ready for the next humongous chips of AI, ML, and we are at the 3 nanometer and 2 nanometer process, we are going to require another paradigm shift. And so with this talk, hope to give you some of the insight and perspective. Whether you're a startup company or investor, you have to invest in new talent because you will need to bring in the new talent in order for you to handle these humongous chips that's coming down our pipeline. So now if you look at the Moore's law, so everybody knows about Moore's law. So what I've done is that I've overlaid the process nodes that is on the left, and basically you can see the transformation and the different microprocessors that's done over the years. So again, why are we talking that Moore's law is slowed down and so forth? If you look on the table on the right, some of the driving factors is that 2D is fast approaching 3D. You know, if you think of real estate, right? When you run out of real estate, the only way is you have to build multi-story buildings. So you can think of 3D IC as that there's real estate on silicon is running out. So the only way for you to pack more functionality is to go upward. And there goes 3D. And then the next thing is that you hear about computing. Computing in the past is always about CPU. Today, computing is not only about CPU, but also GPU and NPU. So we have really expanded the scope in terms of what computing stands for. And then the other things you hear in the keynotes yesterday, the data bandwidth is important because if you have all these chips that you're putting together, the communications across the chips and the bandwidth is a high demand. And then also, we are also switching the way that we are doing design. Some of us are now feeling comfortable. We are doing design on the cloud. And then also you can see that now engineers, we don't have infinite resources. So engineers are being pushed to design chips that's much larger than what they used to do before. And on top of all this, the new challenges, instead of what we always know, power, performance, and area, this is going to expand to new matrices that you have to worry about. Now you have to worry about stress, you have to worry about thermal, you have to worry about the EMIR, and on top of that, you have to worry about packaging. So all these are the new domains that we have to face with when we are talking about AI chips and the large, humongous chips that we are supposed to be designing. So now, here's the things that we have to get ourselves ready for the next transformation. And in this transformation is big, because if you look at where today, how IC designs are done together with the packaging teams, they are just like what happened 10 years ago. In 10 years ago, you have the front-end engineers and then you have the back-end engineers. Today, the design team and the packaging teams are done separately. After the design teams are done, the packaging is done at the tail end of the overall process. But if you look at where TSMC is going with the wafer level packaging, all these things are going to happen much earlier in the cycle, and it's not going to happen after the fact when the chips are fabricated. So when you look at all those requirements, what you see on the right is that to do a 3D IC, you not only need the synthesis engineers or the place and route engineers, now you need to get engineers that know mechanical stress. You need to get engineers that knows thermal. You need to get engineers that knows the EMIR and the PISI. All these things are now is going to expand your entire design team. So you're no longer just confined with just the front end or the back end, but you have to consider all these effects if you're going to do a 3D IC. So if you look at this, what again is that is going to drive the next paradigm shift is going to be the multidisciplinary teams. So if you are talking about team formation, this is a good time to think of how do you really expand your team knowledge to be able to deal with all those new matrices that you have to solve when you're doing the complex 3D IC designs. So now if you look at the summary, what is the fusion trend? So everything is going to go 3D. It's just a matter of time. Actually, 3D IC, if you look at it, 10 years ago, many of us talk about 3D IC. But at that time, Moore's law was still very strong. So it really never picked up. The best that is picked up was the CoWoS. But today, the true 3D is going to come. It's just a matter of time. And once it comes, everything is going to go 3D. So when we do SoC designs, many of us knows that we were integrating blocks. In the future, when you're doing designs, you're going to be integrating chiplets. So your blocks have now grown into chiplets. And to do all this, again, you will need a multidisciplinary engineering team that you have. And then to the bottom, what you will see as a change is this is where the EDA companies like Cadence is doing is to help enable you with the AI ML assisted design flow. So if you look at where the software company can help you with your IC design is to enhance the algorithms through the years of knowledge that we have done chips and use those knowledge to actually help you to make prediction and to make faster convergence for your IC design. So you will see that the methodology that you are used to will be assisted by AI and ML that's going forward. So if you look at this picture, so there are three parts of it. So one, if you dissect the 3D ICs, the software itself have to be able to model this to be able to solve the problems. And then at the bottom is the design related, because when you stack all these together, you have to worry about thermal, power, EMIR, stress, and so on and so forth. Even your sign-off, traditionally you're doing your STA sign-off on a 2D design. Now how do you do a sign-off on a 3D design? So those methodologies and those are going to change over time. And then finally, number three is that you can see from this chart itself, you will need the multidisciplinary engineers for you to be able to solve this problem. So let's go through one by one on these three key points. So the first is this whole AI ML assisted design flow. So one of the things that the Cadence has been doing is to already enhance the algorithms to be able to predict and to be able to help with your overall design flow. So typically what you see here is that the non-numerical methods are typically experience of the engineers. So you might have an engineer that has worked 20 years on the design, and they are very well versed, so they know what type of knobs that they can try and so on and so forth. But what if we transform it to a numerical methods where we can do it more systematically and leverage the software and the computers in your farm to be able to solve those problems? So then basically what you will see is that you will see that the transformation of the design flow will take the intent of the user and then basically to build the ML model and to be able to help you with the overall design flow, hopefully to come up with better PPA numbers than what you have to do with the try and error that you are used to doing in the past. So that's one of the things that we have been actively developing is the solution. So for 3D IC, we've been working very closely with the various foundries to be able to support the 3D IC. So we're happy to announce that we do have a platform that will enable you to go through the entire design process from the chiplet design all the way to the integration of your 3D chips. And then the second one is a change is also going to happen because engineers are now pushed to increase the productivity. So in the past, most of the times engineers are being assigned a block or a very large block, and they go through based on their knowledge, know-how, they create the design flow and try to close the timing. But then now, with the AI and ML in the software, now you can actually try multiple runs, and you can actually use the computers to leverage the compute power and to increase the search space so that you no longer have to do any trial and error by yourself. And then finally, in the future, you will be looking at multiple screens, and the computer itself will be submitting the jobs and be running the jobs for you. So this is what we envision that will help in terms of the IC designers to increase the productivities. So instead of hiring many resources, you can now leverage the same resource but able to handle the multi-designs at the same time. So if you look at where Cadence is that, so we do have a platform in terms of where our AI and ML is. So while many of us are talking about hardware, AI on the chip and so on and so forth, AI ML also applies to this software. So the Cadence AI is basically the overall platform where all the product teams are enhancing their algorithms to put machine learning models, predictions into the platform. So what you see on the gray table here is the product names that has basically been enhanced to take advantage of AI ML algorithms. And then what you see on the color, the center, these are the platforms for the various. So whether you're doing digital customs, packaging, or even the multi-physics analysis, we do have a platform that can help you with using AI ML techniques in your overall design flow. So finally, just to show an example, so this is the Tesla. So Tesla uses the full Cadence solution to design what they call this Dojo AI computer chip. And this is actually in the Tesla today. So we are very happy to collaborate with Tesla to come up with this 3D IC chip. So, ultimately, the proof of concept from, ideas into really putting into chips is real. It's actually starting right now. So I think we are here to really catch the next wave where the AI ML is going to basically lead the entire semiconductors into the $1 trillion market space. So in summary, so if I were to just summarize some of the observation and trends, first, foundries, right? So now you can see that 30 years ago, there were many foundries around the world, and it starts shrinking, and you have down with TSMC and a few handful one. But in the recent years, you almost see in the news that almost every country now wants to build their own fab and foundry. So the fab capacity is going to be one of the things that is going to be challenging to really meet the demands. And the second observation is process scaling. So if you remember Moore's law, when you basically goes from one node to the other, you automatically get the performance. You know, you get the 2x performance and so on and so forth. Today, as you go from one node to another node, you're not getting the 2x performance. So there's a lot of dependency that the software algorithms has to be enhanced to be able to support the performance gain when you go into a different process node. The third observation is, as I mentioned, if you're going to think 3D IC, you have to think of a team structure. And now your team structure will have to consist of multidisciplinary engineers that has mechanical background, thermal background, and basically be able to do even the packaging level. And then finally, for the design flow that you are used to doing with your own recipes of try and error switches will evolve into having the AI and ML to assist you to increase this search space and to come up with a better solution for your design. So with that, I end my presentation and thank you for the opportunity. Thank you.
We are a bit over time, so if you have a question, please discuss with Tom after this forum. So our next keynote speech will be brought by Jerry Chen. Jerry is the Director of Global Business Development at NVIDIA for Manufacturing and Industrials. Over 20 years at NVIDIA, Jerry has led an initiative in scientific HPC, AI, graphics, and founded NVIDIA Inception Program for startups. Today, Jerry will talk about domain-adapted large language model for chip design and productivity. So let's welcome Jerry. You may need a little bit of time.
I think they'll have your file.
Okay,
so
the
you
updated slide?
can
Okay.
control your...
Okay, great, thank you. All right, let me put this down. Okay, thank you.
Okay, welcome,
Great.
Jerry.
Oh, thank you. I guess I don't need this. Thank you very much. Thank you very much. And Don, that was a very inspirational talk. Thank you very much. We certainly are very enthusiastic consumer of Cadence tools at NVIDIA. So look forward to continuing to working with your team on many of these AI and other initiatives. So thank you for that. So my name is Jerry Chen. I'm the Director of Business Development in the Industrials and Semiconductor vertical at NVIDIA. It's always an honor for me to address this community in Taiwan at Computex. Not only because of how dynamic and innovative this community certainly has always been, but also as our CEO Jensen Huang always is very fond of pointing out, Taiwan is the nexus for us to be able to engage with the ecosystem that allows NVIDIA to bring our technologies to the $100 trillion global economy. So thank you for that, and we look forward to doing more with Taiwan and the innovators at Taiwan over the next 5 and 10 years. So what I thought I'd speak about is some of the efforts that NVIDIA's VLSI team has been doing to try to bring AI to enable and enhance the productivity for our own kind of unique workflows. So as I mentioned, we are certainly enthusiastic users of Cadence tools and other tools as well. Some of these workflows are kind of unique to NVIDIA. And of course, since we are developing a lot of these AI capabilities, software tools, and hardware tools, it seems natural, of course, for us to be able to use these tools for us to develop capabilities for our own productivity. And as Jensen Huang is always fond of saying, we ourselves couldn't tape out our chips nowadays, and certainly not at the quality and at the pace that we tape them out without using AI in our own workflows. So just as a touch point, I guess, so Dr. Liu spoke about and showed some videos for some of the fantastic demonstrations that have been very popularly viewed and consumed by people in the consumer space. And I find them personally amazing, and I'm always astonished by the kinds of things that are made available in the consumer space. in the industrial space, and especially for the semiconductor industry, there's obviously a lot of reasons why this isn't quite, it isn't quite enough. It's obviously very promising and it's got a lot of power, but there's a lot of constraints and restrictions that are necessary for us to make it useful in our workflows. Let's see, hang on a second. Sorry, do you have the second version of the slides? I sent an updated set of slides this morning, but maybe that was a little bit too late. I'll continue if that's all we can do, but...
Let me do double check.
Okay, all right, thanks. In the meantime, I'll just continue. We use many of our tools to do a variety of different things to combat some of the issues that are obvious restrictions for using large language models and generative AI models and making them useful for industrial applications. So obviously a couple of things that have always been difficult for people to address is some of them out of the box can be susceptible to things like hallucinations. So they produce results that look plausible and they're maybe grammatically or syntactically correct, but they're semantically incorrect. There are a variety of technologies that we can bring to bear and tools that allow you to use those to be able to control some of these hallucinations. I'll name 3 of them off the bat, and hopefully we'll be able to get to them with the slides that I wanted to be able to discuss with you. But the 3 techniques are, of course, retrieval augmented generation, which is the idea of taking the prompt that comes in, the questions that come in, give it some additional context by pointing it at enterprise data. You can store that enterprise data in a vector database to allow you to do a better job of selecting that enterprise data to give it appropriate context. Secondly, you can actually do domain-specific, domain adaptive pre-training of the actual large language model itself. There's many techniques to do that and a whole spectrum of ways to do that. And then finally, we can bring in some tools that are generally referred to as guardrails. And we have many tools available in our basket of software tools that we call NEMO that should make this easier and to use and easier to consume. So let me talk a little bit about this project that we call ChipNeMo, which is this foundation model and a RAG workflow that's useful for NVIDIA's own engineering services. So number one, we started with a generic foundation model. We actually, in reality, experimented with several foundation models, including our own foundation models. What we published was the work that we did based on an open source foundation model called Llama 2 that many of you are probably familiar with. We took that foundation model and essentially poured in 30 years of NVIDIA's proprietary design data to make that foundation NVIDIA's own foundation model. And that is what is this ChipNeMo model that we spoke about. The interesting thing about that is if you look at the computational cost that's required and you compare the original computational cost for training the original foundation model versus for the domain adaptive pre-training, it's about 2 orders of magnitude less in terms of computational cost to do the domain adaptive pre-training. In some cases, it may be necessary for yourselves or anybody with very domain-specific applications to be able to train the complete model from scratch. But in many cases, we find that just doing the domain adaptive pre-training is sufficient to give you some additional domain knowledge and embed that into your model and then connect that to your enterprise data with the RAG workflows. And then finally, the last step that our team used is the supervised fine-tuning. There's a variety of different techniques. You can think of that as a way of sort of additionally modifying the weights in the model to make it more domain-specific. There's many techniques that I'll just touch on here because I don't think we're going to be able to touch on them later on in the slides. So NVIDIA's actually come up with several techniques that are particularly useful for us, and we've made them available in a variety of different tools. So one would be prompt training, otherwise known as p-tuning, as well as another one that's sort of an automated aligner that's called steer-LM. for ChipNeMo, the foundation model was kind of like the beginning. And again, it needed to be sort of domain adaptive to be relevant for semiconductor designers. We spoke publicly. We have a variety of different applications that we've developed internally. But we spoke publicly about 3 examples of these applications that our own chip designers use. So number one is essentially like a Q&A chatbot that's useful for either new engineers or engineers that are perhaps exploring outside of their space of expertise. I think Don's point about how there's going to be more necessity for kind of multidisciplinary teams is a perfect use case for why this is relevant, so that people can kind of get a better sense across other domains for other team members that they're working with. So that was the first application. The second application was for us to essentially triage the bugs as we go through the development process. We can quickly triage the bugs. And this application alone is estimated to save about 1,000 engineer hours per day at NVIDIA at this point. So a huge productivity boost for us. And then finally, we also created a model that can do code generation. And this is, in many cases, is for kind of proprietary code codes that NVIDIA uses. So for example, we have an internal scripting language that we call Vivid, which nobody outside of NVIDIA really knows anything about. So we, of course, needed to have the domain adaptive pre-trained models be aware of what Vivid is and know something about the specifications, so we can generate the relevant code for what it is that we were looking for. Okay, so here are some of the issues that I think are commonly observed for generic large language model when you don't give it the appropriate context. And this is certainly a good way to get things rolling. You can get a quick minimum viable product working, but it obviously has a lot of limitations. All you're doing here is relying purely on the large language model. And if you're just taking a generic off-the-shelf open source foundation model, it's going to have a lot of limitations. So number one, it doesn't have any proprietary or domain-specific knowledge baked into the foundation model itself. Of course, unless you are continually retraining that model, it'll get out of date. It doesn't have any context for enterprise data that you're constantly updating. And then finally, of course, as I mentioned, it's sort of at risk of all these hallucinations unless you give it the appropriate context and updated data and all the guardrails that are necessary for it to be a truly useful tool in productive environments. So if you expand this out, and this is kind of like jumping to the end, so in addition, so not that loop that I just showed in the previous slide, that's kind of the loop here on the left. One approach for making this much more relevant and giving it a better context so it doesn't hallucinate, and also keeping it up to date, is you simply attach the large language model and feed it during inference time, giving it access to enterprise data. You can certainly give it access to enterprise data just simply through traditional search methods. What's turned out to be very productive in this type of workflow is to make that data available into an embedding model and put that into what's called a vector database. And then you can deal with the fact that you don't necessarily have a direct one-to-one match for the kind of context that you're looking for.
Sorry for the interruption.
Yeah,
the
sure.
new presentation is ready.
Oh,
so would you like to use the new one?
Yeah, that would
On
be...
which page that should we go back to?
So go to slide 3, 4.
The third one?
Something
Okay.
like that, yeah.
Well, we'll actually do it for you. So you have to cue them to do next.
Oh, perfect. Okay, thank you.
you.
Oh, perfect. Excellent, thank you. All right. Okay, so one thing I should mention is that just as a best practice that we've discovered is that it's certainly good to be able to go into a project having some idea of what kinds of outcomes you're looking for. And generally those are looking at these kinds of metrics. Certainly it's not a useful application unless it's going to give you accurate results. Latency is also important because after all these are productivity tools. And then finally the cost of inference is important. So next slide please. So actually next slide please. This is what I was referring to there. Why don't we jump to the next slide after that? Sorry, next slide after that. I kind of adjusted the flow of my talk a little bit, so my fault. Okay, so So back to the KPIs. So specifically for this ChipNeMo project, again, these three metrics, accuracy, latency, and cost, there are very specific things that we found were important for our VLSI team. So certainly accuracy has got to be relevant for our domain-specific tasks. Secondly, as I mentioned, this is using NVIDIA's own proprietary data, so it's essentially crown jewels. We couldn't afford to send this out and to hit cloud APIs, so this is something that we're running on-prem for our purposes. It had to be grounded, of course, in the chip design domain. And then finally, the latency has to be something that would be useful for the engineers that were working with this. And then finally, the cost of development as well as the cost for hosting it, once we handed it off to our IT team, it had to be tractable. It's got to be something that we're able to deploy and scale as more and more users continue to hit it with more and more queries. Next slide, please. Next slide, please. Okay, just to give a little bit of a sense for the types of data that was necessary. So ultimately, we needed to be able to take the domain-specific data and train both the foundation model itself, that's kind of the data on the left, and then finally to also do the fine-tuning that I touched on a little bit earlier. Next slide, please. Okay, so I'm going to go kind of through the journey, if I have enough time, for how you can get these results to be more and more accurate by adding more and more of these capabilities. So this is the base model. Next slide, please. So as I mentioned earlier, the first thing you can do is you simply provide at runtime the context for additional data that you pull out of your enterprise database. Now, that's got two advantages. Number one, it gives additional context, so it doesn't hallucinate so much. And the second thing is that it's more up to date. You don't need to continually retrain the large language model on the left. You can just make sure that your enterprise data is up to date, which it generally is anyway. Next slide, please. The next step after that is the world is messy. So much of the data that is available in your vector database may not be very clean and stored in a structured environment. Oftentimes, it's actually, you're just trying to find the most relevant information. And the best way to do that is to put it into an embedding space and put it into a vector database, so you can find essentially similarly relevant data that's relevant to the query that you've imposed. So that is a big step forward. And then next slide, please. The further step that you can take is you can actually add in ability to essentially rank the results. So I guess the best analogy here is if you go and search for something on the internet, you get a lot of results back. But right now, the internet capabilities of Google and other providers, they're actually pretty good at ranking those. So it gives you not just a list of possibly relevant results, but it actually ranks them in terms of quality. Next slide, please. And then finally, the next thing you can do is you can actually touch the LLM, the core of this model. I'd mentioned all these steps earlier. They're actually not necessarily touching the LLM. You can just use the regular language model that's available through a cloud API. But by fine-tuning them, you can essentially do a little bit of training and a little bit of modification of a few of the layers in the large language model, and that gives you more domain-specific relevance. Next slide, please. There's a whole spectrum of things you can do depending on your requirements and the cost that you're willing to bear in terms of computational cost. But from left to right, essentially you can do some manual tweaking of your prompts, essentially ask the large language model a better question. Many of you might have already experimented with this by playing with online applications like ChatGPT. You essentially just give it a series of questions in order to get the answer that you really had in mind answered. That's a relatively manual thing, and it doesn't add any information to the large language model. So that's one approach. Prompt learning was the innovation that I mentioned earlier that NVIDIA brought to market, where you're essentially taking a lot of labeled data and you're training a little, it's called an LSTM model, and inserting that as a token in order to get a better prompt, essentially. So it's sort of an automated way to generate a better prompt to the large language model. But still, so far, on these left two columns, you're not actually adding any information. You're not adding any knowledge into the large language model. Those are the two on the right side. So the first thing you can do is this parameter-efficient fine-tuning. And that, as I mentioned earlier, is when you can kind of retrain a few layers without changing the weights in the bulk of the model. And that can give you much better results. And then finally, if you really need to get very specific, and this is what we did with ChipNeMo, you can do the full supervised fine-tuning. And there's many techniques to do that. In particular, this innovation that NVIDIA published called SteerLM that does a better job of aligning the answers to what it is that you're looking for. Next slide, please. Okay, so now I'm going to talk about touching that large language model, as I mentioned. So fortunately, the community has produced many, many open source large language models where the weights are available to you. They all have their pluses and minuses, and we've experimented with many of them. But the fact that there is an open community of these community available models or even some commercial models, that means that you can actually get down into the core of it and essentially train that large language model to be domain specific with your own information as well as proprietary. So next slide, please. Now finally, when you deploy it in production, there are many other concerns other than just making it work. You have to be able to have it be scalable. You have to be supportable by your IT staff. And we've tried to do that by kind of hardening and putting into containers a lot of these language models into what we call neural inference microservices. So they're much more supportable and scalable. I won't go through all the details, but essentially you can think of this as like a productized version of a large language model or other functions that are made available through APIs to hit a microservice. Next slide, please. Now, for the evaluation methodology, I think it's important to consider there's again a spectrum of ways to evaluate the quality of the talk, the quality of the RAG workflow. You can use some automated techniques if you have very well labeled data, and then on one end of the spectrum, and then the other end of the spectrum, you can simply use human feedback, which works well, but it's not very scalable. A nice balance in the middle is what we call the LLM as judge, which is essentially taking bootstrapping the feedback that you've gotten from the human data as well as from the labeled data and sort of creating this little LLM that is capable of providing that kind of feedback. Sometimes that's a much smaller model, and this is an open area of research, so that's why I had this sort of idea of the SLM, the small language model, but this is like a good happy medium between the others. Next slide, please. Okay, I'll finish off by talking a bit about some of the results that we saw in our exercise. How are we doing on time? I don't have a timer here.
I think we're running out of it, so
Okay,
maybe...
all right, let me jump. Next slide, next slide, next slide. Okay, I'll just touch on this one and then I'll close off. So just some of the final results that we're very happy to see. So on the left side here, this is the code generation task that I mentioned earlier. A couple of things to point out. So that green bar is the incremental benefit and the accuracy you get by doing the domain adaptive pre-training. So the blue bar is the undomain adaptive raw model, the llama model that it comes from. So a couple of things to observe. So certainly in every case, by doing the domain adaptive pre-training, you get better accuracy. The other thing that's interesting to observe is that the smaller model, this llama 7 billion parameter model, with the domain adaptive pre-training, it's actually matching the accuracy of really the state-of-the-art model here for GPT-4 in this particular case. That was on the left, and on the right side here, this is actually a case that Paul Cunningham at Cadence spoke about. This is in our collaboration with Cadence for just out-of-the-box re-ranking of the data that's coming out of the vector database and achieving this, ultimately, this almost 90% accuracy for top 10 results. Just out of the box. There's nothing to do with domain adaptive pre-training. This is just the ranking of the data that's getting pulled from the vector database is hugely valuable. And again, it gives it a lot more context and a lot more accuracy for the final LLM answers that it provided. So that's it. Sorry for the confusion there. So it was a little scattershot. Next slide, please. I think that was the last one. I'll just close by saying that there are a lot of these capabilities that I described here. We use it ourselves on the NeMo team, on the chip NeMo team, and that has turned into sort of productization in our NeMo frameworks that are available in a variety of different capabilities and tools. So that's it, since we're going over. So I'll just leave it there.
Thank you so much, Jerry. Let's give him a round of applause.
Okay, thanks. Thanks for your patience.
Okay, our third speaker is Jenwei Liang. He is a deputy director from MediaTek. He works in computing and artificial intelligence technology group at MediaTek, and he participates in AI learning accelerator hardware design and algorithm development. As you know, that MediaTek has been supporting ITRI for the very beginning. Especially, they donated a wafer to our members to do some experiments. Today, the Jenwei will talk about generative AI at the edge. Let's welcome Jenwei. Yeah.
Thank you. And hello, everyone. It's my pleasure to share some of the recent progress of the generative AI at the edge. And well, I think most of the people, when we think about generative AI, and the first thing comes to our mind is that generative AI is only possible in the cloud using the data center with thousands of GPU cards. But well, nowadays, not anymore. Now the power of generative AI is already in your pocket on the smartphone and with very limited battery power and also the computation capability and also the memory size. So, but like thanks to the innovation of the AI researchers around the world and also the contribution of the hardworking engineers, and nowadays the generative AI at the edge is not only a possibility, it's a reality now. So next I'm going to share with you some of the recent progress and also the challenges that we are facing. Okay, so this is the first topic. That's the trend of the AI from analytic AI to generative AI, and also from cloud to edge. Well, I think before 2022, the AI models, we tend to call it analytic AI. Well, analytic AI is all about perception and also enhancement. So these AI models, they perceive the data and analyze the data and do things like classification, detection, recognition, and such as the face recognition, scene detection. And they also can do the enhancement, such as picture quality enhancement with AI noise reduction or AI high dynamic range. And not only the picture, not just the image, the video can also be enhanced by like super resolution and also the frame rate conversion, or sometimes called MEMC. So that's what the analytic AI can do. But like starting from 2022, the generative AI has gone viral. And it not only perceives, analyzes, it also generates. It generates images, and also it generates text, and also videos. So that's the general trend of the AI. Here, I'm going to show you some of the examples of what the analytic AI can do. So at the right-hand side, and that's the noise reduction plus the HDR, a high dynamic range. So when you use the conventional computer vision algorithm, well, it does a good job. But still, if you look at the details in this dark area, well, it barely has any details here. But when you use the analytic AI models with super resolution, the noise reduction, you can see the details over here is crystal clear. And also the reflections here on the water. So that's one example what analytic AI can do for you. And this is another example for frame rate conversion, or MEMC. So again, the legacy algorithm, you still can see the video, it's like lagging or stuttering. It's not very smooth. But with the AI algorithm doing the MEMC, the video is a lot smoother. And this is the telephoto sunshot. And this photo is taken by the smartphone powered by MediaTek's Dimensity 9300. Well, my friend who is a photographer, he tells me that taking the sunshot photo is not easy. even with a very expensive the traditional camera, and not to mention using a smartphone. But here we use like, sorry. Here we use a couple of different AI algorithms, including AI HDR, AI noise reduction, AI super resolution, and also the classification, detection, segmentation, all bunch of AI models to make it possible to take a stunning shot like this. But now let's go to the generative AI part. And this is an example of text summarization. And say, for example, if my boss tells me, hey, Jenwei, here is a paper, and please summarize it for me, and then he needs the summary in 30 minutes. And this is the revolutionary paper published by Google in 2017. Attention is all you need, and which is the foundation of the transformer model. So what we can do is use these to send the abstract and the introduction, which have about like 700 or 800 words. And then we can put it into our smartphone and then create the 50-word summary. Can you click on the video over here? Is staff at the back? Oh, yes. So we put this abstract introduction into it. And this is a real demo on the Dimensity 9300. Then like within 10 seconds, instead of like reading the paper for 20 minutes, 10 seconds, it can give you the 50 words summary over here. So this transformer is a new model architecture that relies entirely on the attention mechanism and things like that. So that's what the smartphone can do for you. This is one of my favorite demonstrations. That's the image generation or text to image. And this demo is the world's first real-time text to image generation. And we are using the SDL, Stable Diffusion Extra Large Turbo model. And it also has won the Best AI Demo Award in this year's MWC in Barcelona. So let's see what it can do. Can you click on the video over here? And again, this is a real demo on the smartphone. So as you type in the text, real time, it generates the image on your smartphone. So I want an orangey fluffy cat eating something, a piece of cheesecake. Then you see cheese over here on silver platter, and then you got the silver platter here. And with a top hat, now you got the hat. No, I don't want orange cat. I want a black fluffy cat. So real time, it changed the image to black cat. And not cheese, but cake. And also real time, a cake. Not a silver platter, blue platter. So that's what nowadays the smartphone can do for you, a real-time video generation. And this is another demo of AI eraser and also AI inpaint. And say, for example, I want to erase this lady from the photo. Can you click on this video? So you use your finger to select the regions that you want to erase. So erase, now take care of the shadow. Yes, as you can see, you not only erase this lady here, you also generate image to fill up the blank over there. And the next one is also a demo. Can you click on this video? So like you have a bunch of people over here, and you don't want these people showing up in your photo. So that's what can be done over here. So it not only erase, it also inpaint. So it generates images. So that's what the generative AI can do. Well, so from analytic AI to generative AI, I mean, there are lots of differences and also challenges. So if you look at the model size, the generative AI is roughly maybe like 100 times larger than the analytic AI. And so is the computation per inference that is needed for the generative AI. And also fundamentally, the backbone of these AI models are different. So previously, the convolutional neural network, or CNN, is the very popular backbone. But for the generative AI, the transformer with attention is the major backbone that most of the model uses. And for the transformer, well, if you talk about details, there are some very messy mathematical formulas that you have to calculate, such as softmax, layer norm, things like that. And that's lots of computation that you have to do. So it's very different for the generative AI and analytic AI, and it imposes great challenges. So, but again, I mean, since we can do the generative AI in the cloud, I mean, why do we want to do it at the edge? So of course, the first thing is privacy. You don't want your personal data to be sent out to some other data centers, who knows where it's located. So you want to keep it inside your smartphone. And availability. Again, I mean, we are not always connected to the internet. For example, when you are traveling on a plane, you don't have internet connection, then I still want to have this generative AI capability. So the edge is the solution. And also, of course, also the response time and also the cost. Because using these like cloud services, you have to pay for them. But if you have your smartphone doing this generative AI for you, it basically is free. All right, so let's switch gear to the challenges. So as I said, the generative AI, it's a lot more complicated. So what kind of challenges we're facing? Well, I like to take this example, the large language model on the edge, and what kind of challenges we're facing. So for example, I use this Llama 7B model, 7 billion models. So without optimization, say for example, if you look at the footprint, 7 billion parameters, if each parameter is represented by a floating point, 16 bits, that means you already have 14 gigabytes of the parameter size, and that you have to place on the flash and then load it onto the DRAM on your smartphone. But if you look at the 2023, last year's flagship smartphone specification, it only has 16 gigabytes of DRAM. Well, you say, yeah, it's still larger than 14, but remember, you still have Android operating system that have to run. Also, you have lots of background apps that are running. So 16 gigabytes, it definitely is not enough to hold the 14 gigabytes of parameters. And also, when you want to run the inference, say, for example, you want to have 10 tokens per second as the inference output, then that means you have to run the whole model through the whole 14 gigabytes parameters 10 times per second. So that means you have to load these parameters at 140 gigabytes per second. That's the memory bandwidth to run it and then generate the output. But if you look at the spec of the last year's smartphone, it only has 50 gigabytes per second. So that means without doing anything or doing any optimization, it's basically not possible to run the Llama 7B model over here on the smartphone. So, but earlier, I mean, we have seen that we run the text summarization. Actually, that one is using the Llama 7B model. And also, we can also run the Llama 13 billion models as well. So how are we going to make this happen? And the previous page talking about the memory requirement. And here is the computation requirement. So the horizontal axis is the year, time. And the vertical axis is the complexity or the computation needed to run these AI models. So the line over here, that's the Moore's law. It gives you probably roughly about 1.25 times growth of the computation annually or per year. But for the NPU, the AI processor on the smartphone, we can get better annual growth than 1.25. Or we cannot get around 1.5 times growth per year. And that's because we can, besides the process migration, we also have some innovation in the hardware architecture that can boost the performance and also the efficiency. But that is still not enough. If you look at the growth trend of the NN model, especially for the generative AI, it's like 2 to 3 times the complexity requirement grows every year. So obviously there is a gap between the computation needed over here and also the computation that the processor can offer. So then we need something. That's what I just said in the previous page, some optimization of these models. So we can bridge the gap and make it happen on the smartphone. Okay, I have to speed up. So the optimization we need is really algorithm, software, and hardware, and it's co-optimization. Say, for example, you want to reduce the memory footprint and also the bandwidth. Then algorithm side, there are lots of things that we can do, such as pruning, to prune out those very small values of weight or even 0 values. Then we can take advantage of the sparsity of the weight. And then we can do the quantization. Earlier I said the model, each weight is represented by floating point 16 bits. But what if we can use integer 4 bits for the weight? Then we can reduce to just a quarter of the original weight. But still, I mean, we have to make sure reducing the number of bits with quantization, we have to keep the quality or accuracy of this model the same as before. And after we have done the pruning and quantization, and furthermore, we can compress this data, either weight or the activation, and then we can, again, reduce the memory footprint. And then the hardware needs to support the on-the-fly decompression, so we can do it in the real time. So like by doing so, then we are able to reduce more than 60% of the memory footprint. And also we can gain about 3 times performance improvement. So if you plug in this number to the previous page, the challenge on the LLM, you can see now it's possible to do that. So that's what you need for the co-optimization on the algorithm, software, and hardware side. Okay, I'll speed up a little bit. The next thing I'd like to talk about the image and video generation on the smartphone. Well, I probably will skip this page. Well, just quickly. This is the image generation, the text-to-image generation. And the diffusion model or stable diffusion. Well, stable diffusion model is one of the earliest open source model that can do the text-to-image generation. And I think there are lots of experts over here who already know how it works. But basically, after we train the diffusion model, we can generate image from pure noise into an image that we want with the help of some text input or text hint. And we can guide the model to generate the image that we want. But sometimes just generate an image is not enough for us. We want control. To control what? For example, I'll skip this one. It won't let me skip. Well, here it is saying on the smartphone, and we can generate image in less 1 second. And on the regular, like in the cloud, using the stable diffusion, then it takes about like 6 seconds to do that. So the smartphone can do a very good job nowadays. Again, I mean, generating just an image is not enough. We want control. We want to control the style of the image. or we even want to control the pose of the, say, the figure that we generate. So now, I mean, the interesting thing is that now we can introduce some of the newer technology. Like one is called LoRa, low-rank adaptation. So the way it works is you don't change the foundation model, the diffusion model. That means you don't retrain it. You only train the small LoRa portion. And then, for example, I train it to the cartoon style, or your painting style, things like that. So here, say, for example, originally, the prompt said a cat wearing a hat. It gives you a realistic picture like this. But now we plug in the LoRa, train with the cartoon style. Then we say, oh, we want cartoon style. Then it can change the output to the cartoon style. So also, if you want to create a picture with a pretty lady with blue jeans, black jacket, and a hat, and we also want this lady to have the pose like this, then we can insert a control net into it. Again, we only need to train the control net, and with the guidance of this pose, then we can generate the picture like this. So that means we have better controllability over the image that we generate. I probably will skip this. So here's so the generation is from image to video generation. So originally we have stable diffusion, which can do the text to image, and it cares about the spatial quality. But then we want something moving, not just a still image. So now next we have the animate diff, and that can generate motion pictures. Then we need to care about the temporal consistency. That means from frame to frame, it has to be consistent. So like here is an example that that's a real demo on the smartphone. Now, of course, I mean, everybody knows about Sora. Sora not only has temporal consistency, also has a very good physical rule compliance. That means like the reflection on the water and things like that looks so real. But nowadays, first of all, Sora is not open source, so we are not able to run it on smartphone. But now, I mean, soon, very soon, I think there are some open source Sora called Open Sora. Then we are going to port this Open Sora on a smartphone. And large language model, I just use this page. So large language model, like originally it's just text input and text output. But since like human perception is more than text, like we perceive the world from images, text, or video, or speech. So it's multimodal. So the same thing also happens to the large language model. So now it's multimodality. And what is the challenge of this multimodality on the smartphone? So if we only have a single modality, text only, then basically we just encode the text into tokens or embedding, and we send it to the LLM. It generates the text output. But again, multimodality means not only the text input, we can have speech input, text input, and image input, or even video input, for instance. Then all these different inputs are encoded into different tokens. So now we have speech tokens, text tokens, image tokens, or video tokens. And then we cascade these tokens and then send it into the large language model. So that means the context length, which means the input of this language model, becomes very, very long. So nowadays, if you look at, say, for example, the latest Llama 3, it has 8K context length. If you look at the Google's Gemini Pro, it claims it has like 1 million context length. So then, why does it matter to have a long context length? So if you look at this page, because the complexity and the memory footprint needs. So the longer context length you have, the more complexity it needs. Say, for example, for the large language model, the computation is quadratic. That means it's to the power of 2. So So the horizontal axis is the contact length, and the vertical axis is the generation of the token per second. So you can see the generation speed drops rapidly, like with respect to the contact length. And also the memory footprint needed is linear, proportional to the contact length n. And around this like 15,000 contact lengths, it can already exceed like 12 gigabytes. Well, 12 gigabytes is not a flagship, it's the regular smartphone, the memory capacity. So like adding this text, speech, image, video, contact length together, then it becomes like formidable or it's almost impossible to run it. So again, we need more algorithm to resolve these problems. Okay, I'll skip the risk. We don't have enough time. All right, so here at MediaTek, we provide the total solution to enable the generative AI at the edge. So as I said earlier, I mean, there are so many challenges, and we need the software, hardware, and algorithm to work together to make it happen. So at MediaTek, we have the NPU, which is the hardware part, and it's power and also compute efficient that can very efficiently run the AI models. And also on the software side, we have this NeuroPilot software suite, and that can enable heterogeneous computing. Heterogeneous means not just the NPU, and also the CPU and the GPU. And then algorithm side, we have these auto-optimization tools that can do pruning, quantization, or even NAS, neural architecture search, and also all sort of like optimization that is needed to speed up the computation. And also the MediaTek's NPU, or the Dimensity 9300 series SoC, or yesterday I checked, it still has the #1 in the AI benchmark, and that's the ETH Zurich, hosted by the ETH Zurich. So Dimensity 9300 still hosts the #1 in the ETHZ AI benchmark score. And at last, I'd like to use this video to conclude my presentation. Can you click on the video? Can stop here. All right, thank you everyone, and that's it for today. Thank you.
All right, thank you so much, Dr. Liang, for this informative sharing. I think that's the wrap for AITA Forum, driving innovation with AI on chips. So we see the perfect combination of AI and IC design, and we see a lot of applications of AI. Let's give our speakers another round of applause, please. You guys are incredible. Yeah, and thank you once again for joining us. And if you want to learn more about the organizer of AITA, welcome to check out their official website, or please interact with our speakers later for more exchange of ideas. So that's the wrap for the forum today. Thank you all so much for joining, and have a good day. I'll see you at 3 p.m. again.